Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about the standard Gibbs free energy of formation. Now, I do have a couple of other videos that are related. There's one that talks about the standard heats of formation, and there is one that talks about the standard enthalpy change of formation. Okay, so for this one here, we're going to talk about formation reactions, and we're going to talk about delta G. The other two videos, they do talk about what happens if you're talking about delta H when you're forming a compound, or what's happening when you have a delta S when you're forming a compound. So if you're looking at those other side related topics, you can also check out the other videos. But for this one here, we're going to specifically talk about forming a compound and then calculating the amount of standard Gibbs free energy that goes with that formation. Okay? Let's say we do this by example. So if we're going to talk about a formation reaction, we are going to form something. We're going to make it. So let's say that I would like to make, well, let's make something simple. Let's say that I'd like to make some sodium chloride, solid, right? Just some table salt. Well, if you're going to make this, you have to decide what elements you need to make it. So if I'm going to make sodium chloride, then I'm obviously going to need some sodium, but I'm also going to need some chlorine, right? Because sodiums plus chlorines will give me sodium chloride. Now, the two questions that you have to ask yourself: what is the state? Are they going to be solids, liquids, or gases? And do they come alone? Like, is this sodium just the sodium like 1? Or is it one of the diatomic elements? Because there are a few elements that do like to come in pairs, like O2, N2, Cl2. So when you're doing this formation reaction, you do have to decide if it's going to be a diatomic element or just by itself. So if you look at sodium on your periodic table, sodium does like to come alone, so it's sodium with 1. But like I say, the chlorine does like to come in pairs, so it's going to be a Cl2. The other thing that you're going to have to decide is solid, liquids, or gases. So sodium is a metal. All metals are solids except mercury. Okay, so sodium will be a solid. The nonmetals are a lot more tricky, right? When you look at your periodic table, some of the nonmetals are gases, like oxygen gas. Some of them are liquids, like bromine. Bromine's a liquid. And some of them are solids, like carbon or sulfur. Right, so you're going to have to look at your periodic table, and most periodic tables are color coordinated. So if the symbol is a black symbol, it means a solid. Usually if the symbol is blue, that means a liquid. And if the symbol is red, red symbols tend to mean gases. So if you look at your periodic table, it should have some way of telling you that the chlorine is going to be a gas. So if you're going to do a formation reaction, you know what the product is. You know what you're forming. Then you just have to figure out what elements are needed to make that product. Decide if they're diatomic, like Cl2, or monatomic, like sodium, just comes as a single sodium. Decide if they're solid, liquids, or gases, and then you have to balance. So if I look at this, I started off with 1 sodium, and I ended up with 1 sodium. In the beginning, I had 2 chlorines, but in the end, I only have 1. To fix that, I'm going to put a 2 here, because that 2 tells me that I have 2 chlorines. So 2 chlorines and 2 chlorines. It did mess up my sodium, though. I now have 2 sodiums here, but I only have 1 here. But if I put a 2 in front, that gives me a 2. This kind of reaction, where you're predicting the reactants, where you're deciding if they're solid, liquids, or gases, and you're balancing, is one of the fundamental skills in chemistry, right? You have to be able to predict products and reactants. You have to be able to decide solid, liquid, and gas. And you have to be able to decide if it comes in pairs or not. So I do have videos that cover all of those, right? So if you're doing this and you're finding that it's not feeling comfortable or familiar, you may want to pause or finish this video and then go back and look at my videos on balancing chemical equations, predicting reactants and products. Okay, they will help you quite a bit if you found that this was a little bit hard to do. So this is a formation reaction, right? I am forming my product. Now, I could measure the change in the Gibbs free energy for this, but there are some restrictions. So when I do this, I need it to be in its standard state. I need everything to be at 1 atmosphere and 25 degrees. So if you are currently sitting somewhere learning about this, you are currently sitting under standard conditions, right? Atmospheric pressure is the amount of pressure that the air is exerting on your head. And for most places on the planet, it's 1 atmosphere. Now, it does change a little bit, right? If you have good weather and you have a high pressure go through, or if you have bad weather and you have a low pressure go through, the pressure varies a little, but it's pretty much 1 atmosphere. And it's the same thing for the temperature, right? Where you're sitting now is probably not exactly 25 degrees, but it's probably close, right? Maybe a little cooler, maybe a little hotter. So this is like normal conditions. That's why when I talked about the sodium, I called it a solid. Because under normal conditions, if you had a piece of sodium in front of you, it would be a solid. That's why I call it the chlorine a gas, right? If you were sitting somewhere and you had chlorine in your hand, at 25 degrees in 1 atmosphere, it's going to be a gas. That's what it normally is. And if you had some table salt, some sodium chloride, in your hand, right, a little bit of white salt, it's a solid. At the temperature and pressure that you are currently existing in, it's a solid. Now, if I were to heat that up, I could melt it. But this whole problem is not happening at extremely high temperatures. It's not happening at extremely low temperatures. It's happening at 1 atmosphere and 25 degrees. Okay, the other thing that's important here is that you're going to make exactly 1 mole of the product, and that's it. Now, if you remember back to your days of balancing chemical reactions, you were probably told once, twice, maybe many times, that the numbers that you use out in front are always whole numbers, always, except here. Because now I found something that's more important. Like when you were learning how to balance, the numbers out in front were the most important thing and they had to be whole numbers. But now I'm going to treat this as a part of a bigger problem. And so when I form my compound, I want to form exactly 1. Now, think of it like math. If I told you, and let's squeeze it in up here, that you had 2x plus 4y equals 6. If you wanted to, you could divide all of those by 2. Divide by 2, divide by 2, divide by 2. And you're allowed to do that because as long as you do the exact same thing to the left side of the equation and to the right side, it's perfectly allowed. So 2 divided by 2 would give you 1x, 4 divided by 2 would give you 2y, and 6 divided by 2 would give you 3. Right? It's the same equation, you've just divided everything by 2. We're going to use the same idea here. I really need a 1 in front of the sodium chloride. So what's the easiest way to get rid of a 2? Divide it off by 2. Divide it by 2. Now, just like this equation here, if you divide one side by 2, you got to divide both sides by 2. Same deal here. If you divide one chemical by 2, you've got to divide them all by 2. Now, this chlorine here, remember there was only 1 of them, and usually when we balance, we don't like to write down the ones, right? Let's put the 1 back. So if I'm going to write this as a formation reaction, 2 divided by 2 gives me 1 sodium solid. 1 divided by 2 gives me 0.5 of a Cl2 gas. And 2 divided by 2 gives me 1 sodium chloride solid. So for these problems here, when it talks about the formation of 1 mole of an element from its 1 mole of a compound from its elements at standard state, this is what they're talking about. And if this is the reaction I'm talking about, there is a Gibbs free energy that goes with that. There will be some sort of value. Now you'll notice that my symbol here is a little more complex than this. Because you're happening to do the whole thing at 1 atmosphere and 25 degrees Celsius, because you're doing the whole thing under standard state conditions, I got a symbol for that. Because that's pretty special, right? You did it with 1 atmosphere of pressure, you did it with 25 degrees Celsius. It's special enough that I want to make note of it. That's where the little degree sign comes from. You put in the little degree sign, that means standard state. And because this is a specific type of reaction, it is a formation reaction, that's why we put in a little f. So this is the Gibbs free energy of formation. Now these numbers are so useful that we actually have tables of them. So let's flip over. So right here you can see I've got a table. Basically it gives you the name of the compound and it gives you the delta G of formation. So this is the amount of energy required to form 1 mole of this chemical from its elements. Now you'll notice that the table doesn't give you the full equation, right? I just spent a few minutes talking about how you write the equation. That's because these skills here are something that as a chemist you have. So for these here, if I wanted to write the equation that went with it, the table assumes that you're a pretty good chemist and you can do this. So let's say that we pick one and do it. Let's say I wanted to write the equation that went with the formation of ammonia, NH3. So if I'm going to make some NH3 gas, what elements do you need? Well, it comes from nitrogens and it comes from hydrogens. So I'm going to need nitrogens and hydrogens. Now I have to decide, do they come by themselves or are they diatomic? Should it be N2 and H2? Turns out, nitrogen does like to come in pairs, so it's an N2. Hydrogen also likes to come in pairs, so it's an H2. Now you have to decide solid, liquid, or gas. So if you have a periodic table and it's color-coded, the N2, nitrogen, is a gas, and the H2 is also a gas. Okay, let's balance this thing. You've got 2 nitrogens here, but you've only got 1 there. If I put a big 2 out in front, now I get 2, because 2 times 1 nitrogen gives me 2. So 2 nitrogens and 2. I have 2 hydrogens on this side, but that 2 multiplies in here, right? Originally, there was 3 hydrogens in H3, but now I put a 2 out in front. So that's telling me that I have twice as many. 2 times 3 gives me 6. I've got 6 hydrogens over here, but I've only got 2 hydrogens on this side, and they need to balance. So if I put a 3 in front, 3 times 2 would give me 6 hydrogens. Now, I did go through creating that equation pretty fast. So if you are having trouble writing the formation equations, you really should go back to some of my other videos that talk about predicting reactants and products in chemical reactions and balancing chemical reactions. Okay, they'll help you quite a bit. Now, if I look at this, though, I got the same issue I had before. You're only supposed to make 1 of these, but when I balanced it, I ended up having to put in a 2. Now, whatever that number is, you can divide it off as long as you divide it off of everything, right? If it was a 3, I'd divide everything by 3. If it was a 4, I'd divide everything by 4. Now, there is a 1 here. So if we rewrite, you had 1 N2 gas, but you divided it by 2, so now you've got 0.5 of an N2 gas. Whoops. An N2 gas. My N got away from me. You originally had 3 H2s, but you've divided it by 2. So 3 divided by 2 gives you 1.5 of an H2 gas. You had 2 ammonias, but you've divided it by 2. 2 divided by 2 gives you 1. So this is an NH3 gas. Now, normally, we don't like decimals, right? If you're balancing a chemical reaction and you said 0.5 and 1.5, whoever asked you to balance it would probably not be happy. But in this very specific case, we're willing to accept decimals here because I really want a 1 here. Okay? So this is the formation reaction of NH3. So if you want it to form NH3, here's the reaction. What's the change in the Gibbs free energy that goes with that? Minus 16.5, and the units are here. Kilojoules per mole. That's the change in the Gibbs free energy. Now don't forget, the F stands for formation. This specific reaction is a formation, so we put an F here. If you are looking for the Gibbs free energy for any other reaction, you don't put in the F, right? F stands for formation, and it's only for this type of reaction. If you're not doing a formation, then you can't use the F. and a little degree sign means that this whole thing happened at 25 degrees Celsius and 1 atmosphere of pressure. Okay, so that's what it means to be talking about the change in Gibbs free energy of formation. Now, if you want to use that to actually do some calculations, because you can look at the Gibbs free energy of formation for various compounds and predict the change for basically any reaction you want. Okay, I'm covering that topic in a separate video. It's going to be called Standard Gibbs free energy of formation used in calculations. Okay, so if that's something that you're interested in, you should carry on and cover the next video that goes with this one. And as always, thank you for joining me here at Chemistry with Dr. Clark.